Right, this guy's happy. And this thing is exactly what it did before. Right. So anyway, so this. Oops. Did I do something weird or what? No. All right. Let me just get this paper up. So there's two papers. One's like 2020, I think, and Meyer's not one of them. But Hallett, I guess, is the connecting point. No, none of them are the connecting point. He cites this paper though, so anyway, they're on the same thing. So they have this middle thing is plexiglass PMMA, and then he's got on the surface of it he has silicone PDMS. Right, so like two kind of common polymers, and the silicone he's using. So he uses this silicone that's see. It says what the name of it is here. And you can, it's in the experimental section. It's called so this thing, no, not that. Sigma Aldrich, monomethyl acryl oxypropyl terminated PMS. Simple. So if you go and just Google that, you can get it from, I should have linked that, I guess, but so Gillette is a company that sells siloxanes. So this is the same thing. So he bought it from Aldrich, but this is, so silicon is like carbon, it's got tetrahedral functionality. And then you can make, so this would be like an ether and carbon, so it's a siloxane in silicon. SiO, and then it's just got the two things filled up with methyl groups. So that's silicone rubber, right? If you cross-link it, usually the end group on this is going to be hydroxyl, and then you can condense that into water and it'll network out. So you can take if you take a tetrafunctional Si and put O methyl, like methoxy groups on it, right? And then it'll bond with that OH at the end of the chain, and then you can have a 4-functional rubber from that. It'll make these siloxane chains going up. And the silicone is like has a really wide temperature range of use. So the degradation temperature, because it's got that ionic bond in the backbone, it's really stable. So it goes up to 400 C. So aerospace temperatures. And then the TG for it is something like minus 100 something. So it's got this huge range of use. So it's good for aerospace seals, because you can go into space where it gets really hot near the sun and cold when you're in the shade. Right? So you need to have that for space things. And also bathtub sealant. So it's got like so many uses, right? And it's pretty easy to make. Like to start with sand, then you kind of put it into hydrochloric acid, and then you get functionality on it, go through organic chemistry of it, and finally you can get to this. So the material it's made from is the most dominant material on Earth, sand, So it's kind of like an interesting polymer. It's $5 a pound. So polyethylene is like 50 cents a pound. So it's kind of pricey. Hard to tell why, but basically it's a little bit pricey. Anyway, so this is a common thing, and you can stick, this is an acrylic group. So it's like the same monomer they're going to use to make PMMA is like this same monomer. So you have the acrylic monomer here, and then they do a thing. So when you make latex paint, usually you'd start with like styrene, but you can do it with PMMA too. You take the styrene monomer or the methyl methacrylate monomer and put it in, and then put soap and water and stir it up, and then put some kind of free radical initiator in it. then you make little beads of either polystyrene or PMMA. And then those, because they're small, so they're going to be submicron size. The stir it, the smaller they get. So it's really like a vesicle. If the size of it changes, it's not really a micelle. So you just put soap, surfactant, um, amphiphilic molecules, and it'll surround it, and then you can make these little polymer droplets, and you can make white paint with that. I mean, it's like a kind of like cheap paint, right? So it's pretty easy to do that. That's called a latex, like latex paint. Here he's doing that in an organic solvent. So what he's trying to do here is make model. So this is his surfactant. So supposedly this is his surfactant. Okay, so he puts in the acrylic monomer, he puts in some of this stuff, puts in AIBN, which is it's got a nitrile group in it. And when you heat it up, that breaks up and it makes nitrogen gas. And then it makes two free radicals that are stabilized. So you can initiate free radical polymerization with it. And you can also use it for airbags in cars. Like the airbag in the car has AIBN. You just heat it up a little bit and it makes a huge amount of nitrogen. So it's non-explosive gas. So you can kind of just quickly make a lot of gas with it. Anyway, so that's what he's doing here. That's the idea of the thing. So there's a few papers on this. So originally, so this kind of makes like a model spherical colloid particles. And if it's in water, then the surface has all kinds of charge on it. So you don't want it to be in water. So basically, they do this in tetralin. So you use a tetralin decalin mixture. So these are go over here. Let's see. That guy's acting funny too. Could be me. They have yeah. That's right. I just draw these next in. Still going. Pretty calming. So this is naphthalene. This is decalin. And this is tetralin. So naphthalene 87 degrees C melting point. Tetralin is 30 degrees C, and decalin's 35 minus 30 minus 35 C. And decalin has like a cis and a trans, where the hydrogen sticking off of this thing here can be on the same side for cis or on opposite sides. And when they're on opposite, that's the trans. No, the cis form, when they're on the same side, somehow it can flip to change it can have a right hand or a left hand, it can flip the thing on it. So that's why, I think that's why it's got those isomers that, so it's kind of like you're adding double bonds and it's a higher melting point. Like naphthalene's the thing, it's going to the closet, you're going to Moss, right? So it's also used as a standard in DSC. Anyway, so if you mix these two, they have different index refraction. And it turns out that the index refraction of like PMMA is in between those two. And when you're doing light, they're doing light scattering. So if you do light scattering, the thing is about light scattering is that X-ray scattering is easier to do because the X-ray density doesn't really change that much between materials. So you don't get a lot of contrast. So it's like much lower contrast than with light. With light, the index can go from like 10. So it can go from like 10 to almost 0, right? So, or to 1, right? 1 to maybe 10 or 15. So there's a huge range of contrast you can get with light. And generally things have big differences. So that stuff is really turbid. If it's turbid, you can't get a beam of light through it, so you can't do light scattering. So you have to match up the index almost exactly to the thing that you're trying to look at for light scattering. So that's what they do. They mix decalin and tetralin to get the index to match the PMMA. So they're making these PMMA things, and then on the PMMA they want to have like PDMS silicone sticking off. So normally the thing sticking off would be soluble in the solvent. So this is the one weird thing, one of the weird things about this paper. So, so PDMS, so PMMA is soluble in decalin and tetralin, and PDMS isn't. So it's kind of like the wrong arrangement of things. So it doesn't make that much sense how this works. And they even say like some of this stuff goes into the core and it ends up giving them this gradient in the contrast. So they show a plot of what they think the contrast is of the thing here. So this would be like the contrast for the this is distance from the center of the sphere. Then this is the PDMS. So it's got that index. And then this is the index for the PMMA, and it's got a slope because some of the decalin tetralin is going into the thing and swelling it. Right. So it's got this gradient down to the middle where it's 1, rho 0 would be like pure plexiglass contrast. Right. So anyway, that's kind of one twist of this thing, is that it doesn't look like, so they get stable colloids, but it doesn't look like this thing is really like a surfactant. Like it's a non-solvent for the thing that's going into. So it's like coating, like say you had sugar tablets and you got to coat it with plastic and put it into water and make it, that wouldn't really make a colloid, like it would settle out because the plastic sugar is hydrophobic and it would just not go into, it wouldn't float around. Right. But nonetheless, these things seem to float around. Right. So that's kind of one twist of this thing. Anyway, so what they're going to do, so anyway, the reason they're doing that is because so people want to study particles in solution to study how packing happens and how crystals form and interactions and things, right? So it's basically they have a system that existed, which is PMMA in an organic solvent with this steric acid, polymerized steric acid on the surface. So steric acid is used like for everything in processing. It's like a processing aid to make things not stick together, basically. So it's not surprising they put steric acid on it, but to put this poly 1,2-hydroxy steric acid, it turns out that's a pretty involved process. So they're trying to make a much simpler process to make these beads. And this group isn't the first one to do that. So this is 2020. So it's kind of like 10 years old, this process to make these model beads with PMS on the surface. Right, so not very exciting, but that's what they're doing, right? This group made those beads and then did neutron scattering on it and used the this isn't part of the homework, but used the Ornstein-Zernike function, scattering function, somewhere in here. To fit the data. I don't see it right now. That's a sphere function. Anyway, it's in here somewhere. Oh, this is our paper. This is this is the 2020, right? Anyway, so this is the one we're looking at. It's the one where they did light scattering. So it's nice because this year, and then they use the Ornstein-Zernike and the Perkusiewicz approximation, and then something a little bit more than that to look at the correlations in this. And then they do static light scattering and they do dynamic light scattering. So I'll talk about talking about dynamic light scattering next week, I guess. But so anyway, first the static thing. So last week we had this, and he gives that equation here too. The structure factor times the form factor, right? He shows that somewhere here. P times Q. He says it in the text somewhere. But so this thing doesn't look like P times Q. Because in order to make this work, like if they were all monodispersed spheres, then you put them into solution and you increase the concentration, monodispersed spheres will just make a colloidal crystal. So they make a hexagonal closest packed crystal or face-centered cubic, like the densest kind. And the density of that's like 72% filling volume. In other words, 28% is air. So when you take spheres like marbles and just put them together, you get 28% air. If you just shake them, they'll make an HCP. And these colloidal PMMA particles will do that too if they're monodispersed. So he needs to make the particles polydispersed. right? And I think he gets like a 5% or 8% dispersion in the sizes. The other thing, he doesn't give like the standard deviation of size. He says it's like 8%. He just says 8%. He doesn't even say of what, so it's not exactly the standard way to talk about dispersion of particles. But you'd want to have the standard deviation. Anyway, so because they're polydispersed, you can't just take the structure factor times the structure factor S of Q, which is the organization of it, which is a thing he's kind of interested in, times a form factor P of Q, because there isn't one P of Q, there's a P of Q for every one of these little different size particles, and they're mixed and matched. So you can take any one small particle, one big particle, two the same size, and then the other way around, right? So you have to mix all of them. So he has like alpha and beta. Then these are the amplitudes. So the intensity is the square of the amplitude. So here he takes the amplitude of the alpha, the amplitude of the beta. This is how many alphas, how many betas. So it's basically the square of the amplitudes, but they aren't the same amplitude. So that's going to be the form factor for his thing. And he's going to have to sum. So this is really a double sum over alpha beta to get every possible pair, minus where they repeat, So in other words, if it's particle 1, particle 2, it could be particle 2, particle 1. So you have to kind of divide that by 2, but you can do that here. Anyway, the idea of this is that you're doing this mix and match of every possible particle. So that's kind of the scheme of things. So everything has to be kind of done that way officially. Like even the structure factor has to involve like all the possible combinations of the polydispersed particles of the A alpha beta coordination of the particles. So everything gets to be a little bit complicated. And then he uses this, I think this is usually called a Flory-Schultz distribution or just the Schultz distribution. But it's a pretty complicated distribution function. Here he's using it for the size of the particles. Like the sizes are, and then there's an average size R naught. It's not, I guess he's saying R naught is a mean radius. So it's just the number average radius. And then the Z factor is something to do with the polydispersity. So I guess he gives an equation for the polydispersity. So this is the standard deviation, I guess, actually. So he's got the values. Let's see. This is a weird way to talk about polydispersity too. So it's not exactly the standard deviation. Standard deviation would be the value minus the mean value, that difference squared, divided by the mean value squared. So anyway, he's got his own way of defining everything here. So this is a little bit, this function was derived for polymerization by Flory to talk about the distribution you get if you just like free radically polymerize polymers, and that would be the kind of distribution you would get. So this was derived for chain length of polymers, like molecular weight of polymers, not sizes of spheres. So why he would use this Flory-Schultz distribution here is pretty odd too. So normally, so I asked the question, like for you to take this thing and like plot it. So anyway, take this thing and then plot also the two ways that people normally talk about spheres, would be like the log normal distribution would be like the standard way. So if you're growing things, you start with something small and you're gonna grow larger things. So your population is gonna have a cutoff at the low end, right? And then you're gonna have like a tail of like they could grow to infinity. So it could have a tail. So the log normal describes that kind of thing. Or if you say like you have sand on the beach and you just ground it and ground it and ground it, but you find out that it takes to grind a big chunk of rock takes a certain amount of energy, but the smaller the rock gets, the more energy you have to put into it. If you try to break apart an atom, it's a huge amount of energy compared to the amount of energy for a brick. Okay, so like there's a cutoff point to the amount of energy that the waves attack the sand that leads to the smallest possible size sand that you could have. So it can't go to zero, right? That's the point. So log also can't go to zero. So log normal distribution is a good thing for things like sand, basically anything that's like normal, right? We'll have like the largest size can be pretty big, smallest size is a fixed size. If it's growing or if it's being ground up, right? And spheres are a pretty good example of that. So basically log normal would be like the standard way to look at this. The other option that you usually have is this Gaussian distribution, which is the thing like Gougnier's law is that. So it's also called the normal distribution. The problem with this is that we have a mean value, but this never goes to zero. Like your probability, there's no minimum. So even if so say this mean value is 10, you would have a value at like minus 500. And if it's the size of a sphere, you can't have a negative size. So it has to truncate at zero. So this function isn't good for real things. It's good for something like maybe grade distribution, or sometimes it's useful, but basically not when you're talking about distribution of particles, log normal is better. And if you look at this Flory-Schultz equation, Schultz distribution. I guess it is Flory-Schultz. Yeah, it's Flory-Schultz. He calls it Schultz-Flory, right? Anyway, so this thing looks just like log normal. It's got the same kind of behavior. Flory came up with it. I guess he didn't know about log normal. That's kind of what everyone else would use log normal. And I think you could probably work this function into a log normal form if you wanted. It's got a little bit different shape to it. Anyway, so the idea is for the first question is like take this distribution, take that distribution, take this distribution for kind of the same standard deviation, and then see how they look compared to each other. Like, and I think you'll find out that the log normal is basically the same as this Flory-Schultz, and the Gaussian is quite a bit different distribution, like how the particle size distribution would look. Anyway, so that's one thing in this homework. So anyway, so he's got this is just a Fourier transform for an object that's rotationally averaged and spatially moved around, right? So like kind of like the Gougnier particle that's smeared out. So if you take the density of the spheres as your contrast, and then this is a Fourier transform of that to get this Q amplitude factor. And then when you do that averaging, I guess it's called the Flory-Bessel transform or something, Fourier-Bessel. But so, and it's also, I think Gougnier kind of came up with this too. So there's some other people that he names everything in here anyway. But so anyway, that's the amplitude. You square that to get the intensity. This can go plus minus. The intensity can only go plus. You have to square it. That's one way to look at it. But so anyway, so then he ends up, so he has this intensity that he calculates, then he has the structure factor. So it's going to be the form factor times the organization, the structure factor. Then the structure factor can be calculated also by this kind of sum of all the sizes, this SM. Or you can, let's see, so what's the difference in these? That's one of the questions. And I remember sometimes and don't remember. All right, so if you had the size distribution, so formally a normalized, so if you use a normalized average form factor, so instead of doing this accurate calculation of it, you consider an averaged form factor for all the polydispersed. So you say there's one monodispersed sphere that's an average of all the polydispersed spheres. That's the form factor. And if you use that, then you get a structure factor, this SM, that would be the effective structure factor from this, ignoring this kind of contrast thing, the amplitude function, right? So basically, SM is what you would do experimentally if you measure the dilute solution spheres. So you measure the dilute solution spheres where S is 1, then you get that average P of Q, the average form factor for the dilute solution, and you divide the intensity by that P of Q, then you get this S of M. And so that's experimentally what you should get, and he can calculate it also using this equation. All right, so he can calculate it the way he measures it, and he can also get the actual measure for the overall irrespective of it. So if you ignore the particles, you can also calculate it another way, this S total. So ignoring the polydispersity in particles. So there's like 3 ways to get the S of Q that he gives at the end here. he gives in this plot. S of Q. S of M is how you kind of experimentally would get it. And the dots are the experimental values, and they agree pretty well. S totals this thing, S totals if you ignore that the particles have different sizes and just calculate their positions in space. And that doesn't match up very well in the second order, third order peaks. And then S monodisperses if you ignore the dispersion of it altogether. Right, so S total includes the dispersion for the structure factor, but not for the particle form factor. And S monodisperse ignores all the polydispersity. So anyway, he's got those three things. So he's got a pretty complete analysis of this thing in a kind of complicated mathematical situation. You know, this is his fit to the form factor using that equation when S of Q is 1. And he gets a pretty good fit to it. And then he's going to use that average P of Q that he get this fit to, divide the intensity by that, and get this S of Q for his experimental. And that he can calculate that also like 3 ways. Right. And the way he thinks works here. So that's pretty good. So all right, so to get this S of Q, the structure factor thing, he goes through a long and tedious kind of thing here. That's not really decipherable. So we can tell the distribution function, and then the dynamics I'll talk about after. Then where's this thing? I guess it's just at this beginning. So he says how he gets this using the Ornstein-Zernike equation with the Perkusiewicz closure. And then is that it here? There's more to this somewhere. So maybe there isn't more of it. Right, so let's just leave it there then. There's not more to it. So we have that. Then so anyway, so then there's this business of the time dynamics of this thing. So so I'll talk about this more next week, but basically with the so you can do this on the same machine. So he's got a laser. So it's collimated. The beams are all going in the same direction. You know, they always say like focused is a laser, but a laser isn't focused. If it was focused, it wouldn't be a laser. So lasers collimated means that the beams, the independent components of light are all going in the same direction. Focused means that they come to a point. So laser isn't focused. Right? So collimated is what you get if you have the sun and you're like a million miles away on the Earth, and the sunbeams are all collimated. They come in a straight line. So you get shadows. Right? If it's focused, you don't get that. You don't get like shadows and things. Anyway, collimated is good for scattering because you're going to talk about like the angle. So you need to have one angle. You think there's a focus beam to do scattering. Right? So that allows you to define the angle. And then monochromatic. Right? So when you have that, so like 1960 being done with a laser, then you could do this dynamic light scattering. So around like 65, 69, dynamic light scattering came about because you have lasers. And what happens is when you, if you have a bunch of colloid particles, like these spheres floating around, they're moving and the beam's going through the sample and you're picking up with a detector here somewhere. If you look at the intensity that you get from that, it isn't just a flat, you have an average intensity, but the intensity is actually doing this. It's like fluctuating around. And it turns out if you have big particles, the fluctuations are like slower. So this is time. And if you have small particles, the fluctuations are like smaller. It's like basically there's something to do with how that fluctuates. It gives you the size of the particles. And basically because the particles are flying around and they have the diffusion coefficient, the KT over 6 pi by the hydrodynamic radius. That's the Stokes law. So basically, you can analyze that fluctuation of the light to get a diffusion coefficient. And then from that, you can get the size, this hydrodynamic size of the particles. And it's a pretty simple thing to do. Like it's pretty fast. You're going to end up with a correlation function. I'll talk about that like next week. But basically, you can get this diffusion coefficient. So that's what he gets. And from that, he can get the hydrodynamic size of the thing. So in this case, so then the scattering is a function of angle and also a function of time. There's also this time component, and the structure factor has a time component to it, right? So he's saying that he can get by fitting that, he can get the diffusion coefficient using Stokes-Einstein, and then he's saying his diffusion coefficient is going to be like this. It's going to have the average measurement that he can get from this experiment. So he gets an average diffusion coefficient from that measurement, and it's going to be that average times these two numbers, HM and SM. SM is the thing we had before, which is the intensity divided by the average form factor. So it's like how the structure of the particles, right? The organization of the particles in space in Q, right? So that's this SM of Q. So it's how the particles are organized. And then let's see. And then where's that equation? So this thing, the thing on the bottom is the thing we already measured, but he already measured that with a static measurement on the same machine. And then this HM is how, if you have one particle and then it's moving around and you put another particle in, it kind of interferes with that particle. So you have to consider like particle alpha, particle beta, then all the possible combinations of alpha and beta in the system, the same double sum of every possible pair of particles to get this thing called the hydrodynamic factor or something. What does he call it? Stokes-Einstein, Does he say H? So this is the hydrodynamic function. So it means like the motion, it doesn't have to do with water, but it has hydro in it. So hydro must mean something like flow. Basically, how those interfere with the motion. Like when you pack things together, they're going to be interfered with, right? So this H of M is kind of how the thing is organized in a dynamic sense, like how the organization of it impacts the motion of the particles, right? So he wants to get that H of M. That's the thing he wants to get here somewhere. S of Q. So this is showing, so that function again is like the diffusion coefficient is going to be this D0, the average one, and it's going to be divided by the form factor and times this H of Q, whatever it is, somewhere here. So divided by the form factor. So if you can measure the form factor, then this diffusion thing should be like 1 over that. You know, so that's kind of what he shows here. He's got the form factors S of M. It's here. Here's the diffusion coefficient divided by the individual average one. So this thing should end up being H of M over S of Q. And then he can show that this thing is 1 over S of Q, kind of, more or less. In other words, where this peaks, this dips. So this is just showing that equation kind of works. And then from that, he's going to say, well, since that works, then he can look at what H of M is, right? Like, what is this? Like if you have one particle shaking around due to KT, and then another particle shaking around due to KT, how does that other particle impact the first particle? And as you increase concentration, you have to consider a gazillion other particles interference, right? So this is his H of M, and then he presents a theory to fit this thing. And it doesn't work exactly. It kind of works. So this del gamma theory kind of works. Kind of shows the same thing, except that it doesn't match. So it matches the first peak kind of okay, except it's too high. So he has to scale it down with this factor A. So he brings it down to match it here. Then when he does that, he finds out that it doesn't match this peak. So he has to shift this peak a little bit. And that's the other factor alpha. So he's got like two factors to correct a theory. So these are two empirical correction factors that he puts in. And when these factors are 1, he has the theory. So he has a magic number. So where these go to 1 is at 45 volume fraction of these spheres. So 45 volume fraction, the thing behaves the way this del gamma theory says it should behave. And at lower, he's getting too low of an amplitude, and at higher than that, he gets too high of an amplitude. And at lower, he gets the second order peaks in the wrong place to the left, and then it's above that is to the wrong place to the right. Right, so he has two empirical parameters he gets, and he finds out a magic concentration 45% where the world is right. I mean, that's the theme of this, right? So, and he can get, with that, he can get pretty good fits to all the data at all different concentrations. Right. By the way, the fit 60% is actually like a solid. So things actually gelled up into a solid. So anyway, so it's an involved paper. So one question that comes out of this scheme is like, why 45%? Like, what's magic about 45%? He doesn't say. Like, he doesn't say why. But there are some magic numbers for spheres. Spheres are like pretty well studied. So you have, let's see. I think I wrote them down here. Maybe I didn't. So you have the percolation. So when you have spheres, so you increase the concentration. At some point, they percolate. Like they'll form you can follow a pathway through the spheres in the system. So that's like a gel point almost. That's 30%. That's around 31% for spheres. And then there's also this HCP lattice size. In other words, if you totally pack the spheres tightly, then you're at 72%. Right. And so 45 is kind of between percolation and total packing of perfect spheres, monodisperse spheres. Right. So there is some, it's within the range of that something could be going on. You know, so the question is like what? So these aren't perfect spheres. These are these shows a picture of that here. These are like, this is what he shows. So the reason this is a gradient of yellow to blue is because the solvent dissolves the PMMA in the middle. Supposedly it's a solid piece of PMMA, like a bead, right, of 250 nanometer, so a quarter of a micron diameter. Right, so a hair is 50 microns. It's like 100th of a hair is 200th of a hair. Picture your hair divided by 200. That's what the size of these are. You know, so anyway, but the middle is like jello because it's kind of swollen with the solvent, and the outside is like a rubber coating on it, like a silicone rubber coating on the surface of it. That's not soluble in the polymer. So you'd think that rubber coating would be like impermeable and nothing would happen to it because it doesn't interact with the solvent, right? The other thing is that, so how does this exactly work? So these aren't things in the paper, right? So basically, you have to kind of wonder after looking at this for a few minutes that, so he starts with the monomers, like some monomers floating around. And he's got this PMS polymers, 10,000 grams per mole chain, and it's got that monomer on the end too. So supposedly the idea is like all the monomers, you know, if it was a latex, all the monomers would go in the middle, this surfactant would go on the surface, and then this thing would polymerize and the whole thing would go to like the solid polymer latex with surfactant sticking on the inside. Right? That's kind of the scheme of like making latex paint. Right? So the problem here is that even when he makes it in, he also makes it a solvent. He makes it a solvent for both components. So it doesn't actually, everything's in solution, you know. So how this happens isn't exactly explained, like how you get the structure. He claims he ends up with this structure, but that's kind of solid. And he's got these things hanging off, right? But so what's the surface density of those things, right? In other words, so its surface density matters because if they're far apart, then they'll coil up, right? They'll coil up and make like either a good solvent, it's like a 5/3 coil or a 2 coil. Like df is 5/3, df is 2, right? If they're packed closely together, then they'll make this kind of brush conformation. It'll be straightened out to some extent, right? So this is the option that he likes, because this option of the brush conformation is what he likes, because from his complicated fit, he finds out this. He finds out that so a core and shell model, the core is this diameter, this is the shell. The shell is 37 nanometers, so 370 angstrom, right? And then he says, functionalized projected length of approximately each unit of PDMS, like a monomer of PDMS has a 32 nanometer, so 3.2 angstrom length, and then the molar mass 74. You can calculate that so the contour length, in other words, if it was a brush, if it was totally straightened out, it would be 46 nanometer. If it was perfectly straightened out, PDMS sticking out. It's like PDMS is an extremely flexible molecule. So perfectly straightened out PDMS is pretty weird to start with, right? So it's like one of the most flexible molecules, so polymers. So he gets 35. He's only like 10 off from the so almost perfectly straightened out chains, and until he gets to he packs it up till it's almost a glass, so it turns into a jello thing, and then all of a sudden, no, it's because the spheres are packed together. So it's a jello of the sphere itself. Then these jello oval ball things are going to come together and make another jello, like a larger scale percolated solid thing. So when he does that, he says that the surface like layer dumps, like the size cuts down quite a bit. And in the meantime, his sphere size is just constant. So this you have to kind of look at a little bit carefully. It's not very hard to do this. So you have 46. Let me see. So you have 46 nanometer extended length, and then you have to look up like what's the persistence length of so 5.3 angstrom, 0.5 nanometer persistence length, and 2 times that is like 10.6, right? 10.6 angstrom. So you have 460 angstrom divided by 10.6 angstrom ends up giving you like 45 or something, right? 45 Kuhn units in a chain, right? And if you take 45 Kuhn units, so the square root of 45 times 10.6 would give you like the Gaussian size of that thing, right? So that's much smaller. That's much smaller than any 35 or whatever he has, right? So 45 square root is 6, and then times 10 gives 71. 71 angstrom, so 7.1 nanometer, right? So I mean, that's not like, so Gaussian is like way down here, right? So you say, well, maybe it takes up some of the solvent, maybe it's expanded coil. So you get 45 to the 3/5 times 10.6, which gives you a little bit better scenario. So the expanded coil, 5 divide, and then 10.6 times. So you get 104 angstrom. So that's 10.4. So that's still like off scale here. So any kind of solid PDMS, and PDMS is insoluble in the Decalin tetralin, so it can't be an extended chain to begin with because it's not soluble. It's not in solution, right? So anyway, so this thing kind of falls apart at this point. It means so if his shell thing is wrong, then basically everything's wrong, despite his having good error bars. But I mean, so it's a pretty elegant thing he's done, but this point seems to be, first off, as far as I can see, there's no possible explanation for why it would collapse when you get to the concentrated thing, except that something's messed up in the fitting. And secondly, the value he gets, which he's pretty excited about because 35 is pretty close to 45 or 46, that number doesn't seem reasonable at all. Like it's totally right? It doesn't make any sense. So you would have an insoluble polymer. The whole operation is pretty weird. You have an insoluble polymer coating a soluble polymer, and that somehow becomes a colloid, and then basically you get a shell that looks like that the polymer chains are fully straightened out. The PDMS, it kind of doesn't make it for me. Like I don't see how that's even possible. And if this isn't possible, then nothing that he said you could believe. You know, it's a really complicated analysis, and you kind of believe him up to this point. Like this is where I think, because the size of the sphere could be anything, but the size of this, if he knows the molecular weight, that's a fixed possibility, which isn't within the realm of what he reports. Anyway, so that's kind of one thing to look at. That's what this question is. It's not an easy homework. Let's make the size of it. That's this question. D E is, and then what this is just a hypothetical, like say he was right about the 45%. What could that possibly mean? He doesn't give an answer to that. So, but you have some things like this percolation number is 31%. This other one's 72. Say you had 31, and then if you put a rubber coating on the things, does that change could you get to a higher concentration if it's got a rubber coating on it? I don't know. You know, or rubber coating that can that can contract like this, like this is I think it's a 20% reduction in size. So, and that 20% is on the perimeter of it. So that's a lot more volume than 20% in length cubed. Right, because it's at the surface of it's where the largest contribution of the volume is. So a 20% change there has a big change in the volume fraction. So it could be that that's actually the 31% adjusted for this kind of weird expansion contraction thing. I mean, that's possible. Anyway, so I wanted to wait, that's kind of what this homework, it's not a great paper in the sense that it's not very exciting, but basically it's good to kind of look at some of the things, the way people use things, especially static and dynamic light scattering. The only difference, I mean, light scattering can be analyzed the same way that X-ray and neutron scattering can be analyzed. And that's kind of what he's doing here. If you get into the condition, so the difference is that the contrast can be so much higher that you get this situation. So everything in here is exactly the same as if you were doing neutron or X-ray. The difference is this, like, if you have your sphere, so if the index here is much larger than the index of the solvent, then you get like reflection off it. And you can also get this thing, like it can go in here and do this thing and then come out. So you can get internal reflection. So when the index difference is high, that all has to be accounted for. You have to trace every one of those beams, and that's called mute. So that's to be avoided at all costs, you know, because the analysis of that is just the one thing. So you can't analyze any other more complicated thing really. I mean, you can kind of say, well, it looks like, so it's always the approximation is going to be this Rayleigh, how would you spell Rayleigh Gans spell approximation, which means that your index difference is low. Right. So you can ignore all that and just say that this thing acts like a rock that gives off waves, and the waves interfere with each other. That's like Bragg scattering. That's X-ray scattering, neutron scattering. Because then in those cases, the index is really small, right? Exceedingly small. The index difference. So anyway, me scattering, stay away from it. It's bad for you. Rayleigh-Gans, good for you. Right? Rayleigh-Gans. But so anyway, that's kind of where that stuff is going. One other thing. So this is all. I got 5 minutes. You can't take that from me. Right. Oh yeah. Okay. All right. So So he shows this, right? So this is the dilute. And then, so the dilute has this, because of spheres, it's got peaks in it, right? And then he's looking at this, so that's the form factor. And then as you increase the concentration, you get this peak. That's the structure factor that has to do with organization. So it's kind of like this times, so P times S gives you this final answer that you have. Form times structure gives you that thing, right? So I mean, you're hoping that this would be one and then simply analyze, or that that thing's one and this is simple to analyze. Neither one of them is simple to analyze, but anyway, so when you're convoluted, it's worse. Okay, so this, and then with the RPA that we had before, so let's see if I can do this. There. All right, so this is the data we got from RPA. So we have basically, if you take intensity divided by concentration, as the concentration goes up, you get this screening effect that comes in. This business of the sheet or whatever. Like you can't see the chain anymore, so you lose resolution, so it's constant. And then this intercept over here is a measure of the second Viral coefficient, or the osmotic compressibility. Right. So anyway, what I wanted to show you is that it's the same thing here. So in this case, as you increase concentration, this intercept over here drops just the same way as it would drop here. If you take the raw one and divide the higher concentration ones, you get a structure factor for the RPA that looks like that. It doesn't have a peak in it. But this part over here, so this is your non-woven, this is your woven fabric. So woven fabric has a structure, in other words, there's a spacing of the fibers that's fixed. This one that's smeared out, so you get this kind of thing like that. But this part is the same. You can still get the energy of interaction between the things as you increase the concentration, like the second Viral coefficient, right? So the same analysis you can do here. When you use these, so you have this other feature. You'd say like, I have a peak, I have an amplitude, I have a position, 3 numbers. And then I also have this intercept, 4 numbers, right, in this thing. Versus this thing has 1 number, just how much does it drop down, right? So, but it turns out that if you use this use the Ornstein-Zernicke in some kind of closure like Perkus-Yevik or Born-Green, then all these numbers, like the peak position, the breadth of this, and the intercept here are decided all by 1 number. So that's what that equation does for you. It gives you 4 features by 1 number, right? So that's kind of powerful. So that's why it's thought of as like important. You know, I mean, you can get a lot of features from 1 magic number, which is just a simple number, like how things mix and the energy of interaction. You can get the same thing from a mean field, but it's not as satisfying. Like you can't predict the whole curve. Like these are fits with 1 number, like all those lines going through the data. So basically, things on a large scale look the same, and then there's details as you get to smaller and smaller scales. And then they go to the same when you get to just 1 fiber, again, or 1 atom or 1 sphere. Right, so they're the same at really small, they're the same at really big, and in between is where the action is for like the packing of the things. Right, so these things look like they aren't connected, but they're the same thing. It's just that in one case you have organization, the other you don't. So anyway, I wanted to show that. That's all I'm going to say about scattering, I think. So it's good. Anyway, any questions on that stuff? But hopefully it's, I mean, it's kind of a tough paper to look at because it doesn't have any kind of meat to it, you know, but basically it's good because it covers subjects. It kind of shows you where people can go with it. And also maybe there's some flaw that you can pick out in it. And in the final results, some of it doesn't make sense. So it's good to look at. All right, so have a good Easter. That's about it. That's all I got today. So oh yeah, that tour was really good. All right. The tour was 3 hours. Yeah, and all it was 1 plant, but it's unbelievable that one place, all they do, like the stuff you buy at Home Depot, the 3-wire cable, they make all kinds of cable like that, but it's a pretty big time operation. I mean, it's interesting to see. Anyway, we did spend 3 hours there, and I thought it would be like 20 minutes. So it's good you would have missed the class. You would gone to that, but.
I missed my class.
Yeah, I mean, it was like, it turned out, and the guy was like, we were the only people who have ever toured the place. But he was like pretty psyched about it. All that tour, whatever that had built up over like so many years, yeah. But he's like ready to retire, so it's kind of funny. I mean, he actually built the plant, you know, so he like From-
The guy, the baby that's worked.
He basically built the plant, yeah, and it's a big plant. I mean, I think they have like 10 different lines doing all different kinds of wire stuff. It's a lot more involved than what you think, you know? But anyway, they're doing multi-layer coating extrusion too for the coating of the wires. So
Specifically wires like hollow tubes.
it's hollow tubes, but there's an outer tube and an inner tube, and there's a paper tube, and there's like 3 wires that come in all at the same time. And they're doing like 12 of these at once on a line, you know, it's pretty cool. Yeah, it's kind of pretty, and they start with copper, like chunks of copper. And plastic pellets, and they end up with a wire at the end, but. So I think it's kind of an interesting place to look at. It did take 3 hours, though. It's weird.
Again.
Yeah.
Yeah, I have to use.
You too.